Hello and welcome to this episode of Kinemarc's tutorial on algebra. In this video tutorial, we shall test our understanding and revise a few concepts under the principle of mathematical induction. Basically, we know that mathematical induction is a technique that is used to prove various assumptions in mathematics, and it has a few steps. The first step is that you show that the assumption is true for one iteration, and then in the next step, you show that if any iteration is true, then the next iteration is also true. So we can think of this as something like a domino effect, that if you have a stack of dominoes or even a stack of cassettes or a stack of notebooks arranged vertically one after the other, and then you just push one, the domino effect that will cause all the stack of or all the cassettes or all the books to fall. And so we shall apply this knowledge or this phenomenon in the concept of the principle of mathematical induction. So with all I've said, in terms of numbers, the steps to follow. In step 1, you show that for the first case, usually we assume n to be equal to 1. So for the first case, if n is equal to 1, we perform the computation using n is equal to 1 and establish that indeed it is true. After doing that, then we assume n now to be equal to k. And then we substitute the value of n with k, and then we assume that that equation we have is also true. And then finally, we prove that it will also be true for n is equal to k plus 1. So let me go over the steps again. In step 1, you prove that the iteration is true for n is equal to 1. And then step 2, you first assume n to be equal to k, and then you do your substitutions and assume that value or that equation is true. Then in step 3, you substitute the value of n with k plus 1, and then you establish that indeed the iteration is true, and that will confirm that the proof or the equation holds for any value of n. So let's try out a few numerical examples. So example 1, example is that we should prove that the expression 3 to the power n minus 1 is a multiple of 2. So from what we know so far, we must first prove this iteration using n equals 1. So for when n is equal to 1, we shall have 3 to the power 1 minus 1. And this gives us 3 minus 1, which is equal to 2. And as we know, 2 in itself is a multiple of 2. So we go to the next iteration where we have n equals k. And so this one shall give us, by substitution, 3 to the power k minus 1. And this is basically 3 to the power k minus 1. So we shall assume this value to be true. So after establishing this assumption, then we shall go on prove for when n is equal to k plus 1. And so by substitution, we shall have 3 to the power k plus 1 minus 1. And this, from the law of indices, can be rewritten as 3 to the power k multiplied by 3 and then minus 1. Now, we can express this 3 over here as a value in terms of 2. So this is going to be 3 to the power k times 2 plus 1 and then minus 1. So from here, we can see that we have 3 to the power k times 2 and then plus 3 to the power k minus 1. This part is a multiple of 2, as we can see, because 2 is multiplying a certain value 3 to the power k. And then this expression we have over here is valid because when we had n equals k, we had the same value. And so we've established that this value is also true. Thus, it can be concluded that indeed the expression 3 to the power n minus 1 is a multiple of 2. So this is how you go by it. In some cases, you would have to analyze it logically and by inspection so that you would see how to break the equation down to help you arrive at the correct conclusion. Example 2. But before I come to the numerical example 2, let me just go over something briefly here. Now, a common trick usually is to write the n equals k plus 1 case in two parts, with one part being the n equals k part, so what we had over here, and then the other part can be checked to see if it indeed holds for the assumption. So now back to example 2 is that you should prove by mathematical induction that 1 plus 3 plus 5 plus the sum of these odd values plus the expression 2n minus 1 should give us n squared. So the first step in this iteration is to prove for when n is equal to 1. So when n is equal to 1, we shall have 1 is equal to n squared, and we have our 1 and we have our n to be 1, and so we have 1 is equal to 1 squared. This is indeed true. Now the next iteration is that we must prove for when n is equal to k, and then assume that that equation is true. So we have, by substitution, 1 plus 3 plus 5 plus the sum of some odd values, and then plus 2k minus 1, giving us k squared. This is an assumption, and we are assuming that it is true for this purpose. After this assumption, then we shall prove or derive an equation for n equals k plus 1. So for n equals k plus 1, by substitution, we shall have 1 plus 3 plus 5 plus the sum of some odd values plus 2 into brackets k plus 1 minus 1. And this should give us k plus 1 squared. Now from the assumption above, we can see that this values over here, or this summation over here, is indeed a summation that will arrive at k before you get to k plus 1. And so we can substitute this part up until the last term with k squared. Let me take that again. We can see by inspection that the summation in terms of k plus 1, or the expression for k plus 1, is a summation of some values up until the value k before you arrive at k plus 1. From that realization, we can substitute the summation of all these terms up until the last term, which is k plus 1, with k squared. So this will give us k squared plus 2k plus 2 minus 1 giving us the expression k plus 1 all squared. So let's expand the left hand side of the equation and then the right hand side of the equation as well to see what we shall get. So we have k squared plus 2k plus 1 giving us, this is k squared plus 2 times k times 1, 2k, 1 squared is 1. Now by comparison, we can see that the left hand side of the equation is equal to the right hand side of the equation. Therefore, we have proven that 1 plus 3 plus 5 plus the sum of some odd values plus 2n minus 1 equals n squared is true for all values of n. So let's go to our third numerical example. Now in this example, triangular numbers are numbers that can make a triangular pattern. Alright, so let me just sketch what the question is trying to say. So these values are triangular numbers: 1, 3, 6, 10, and 15. They are a sequence of triangular numbers. Okay, so this is the question. By mathematical induction, we should prove that the nth triangular number is t of n, or tn is n multiplying the expression n plus 1, all divided by 2. Let us number our sequence. So we have 1, sequence 2, 3, 4, 5. So we have to, even before we do the proof, generate an expression. And by inspection, we can see that the sum of the first entry in the sequence and the second entry in the sequence gives us the number of dots for the second entry in the sequence. Similarly, the sum of the first entry in the sequence and the second entry in the sequence and the third entry in the sequence gives us the number of dots for the third entry, or the third triangle. Let me just take that again. By inspection, we can see that 1 plus 2 gives us 3 dots. 1 plus 2 plus 3 gives us 6 dots. 1 plus 2 plus 3 plus 4 gives us 10 dots. And then 1 plus 2 plus 3 plus 4 plus 5 gives us 15 dots. So we can deduce that a general expression for finding the nth triangular number is to add 1 to 2 to 3 to 4, following the same common difference up until n, and that shall give us the expression n multiplying n plus 1, and all divided by 2. So we shall prove this for when n is equal to 1. That shall be our first iteration. So we are going to have 1 is equal to 1 multiplying 1 plus 1 all on 2. This is indeed valid because 1 times 2 is 2 and 2 divided by 2 is 1. Then next, we shall make or continue the iteration for when n is equal to k. So by substitution, we have 1 plus 2 plus 3 plus 4 plus the sum of numbers with the same common difference plus k by substitution equals k plus 1 all divided by 2. We assume this iteration to be true and then repeat the iteration for when n equals k plus 1. So we shall have 1 plus 2 plus 3 plus 4 plus sequence members plus k plus 1, giving us the expression k plus 1 multiplying k plus 1 plus 1 all divided by 2. Now this is quite similar to the very first example we did. Here you can see that the sum of entries up until k is contained also in this sum of entries up before k plus 1. You can see that k shall be included in the terms of this sequence. So by comparison, we can equate 1 plus 2 plus 3 plus 4 plus a continuous sum of sequence members with the same common difference to be equal to this expression k into brackets k plus 1 all divided by 2. So by substitution, we shall have k multiplying k plus 1 all on 2 plus k plus 1, which shall give us k plus 1 multiplying now k plus 2 all divided by 2. If you want to get rid of the denominator 2, we shall multiply through by 2 to give us, let's expand both sides of the equation. We shall have plus k plus 2k plus 2, and this shall be equal to k, the expression k plus 1 multiplying k plus 2. So we shall have k squared plus 2k and then plus k plus 2. So now we have k squared plus 3k plus 2, giving us another k squared plus 3k plus 2. Now we have our left hand side of the equation equal to the right hand side of the equation. So we've indeed proven that by mathematical induction, the nth triangular number is given by n multiplying n plus 1 all divided by 2. Our first iteration shall be set to 1, and then we shall do substitution to confirm that a times b all to the power 1 is equal to a to the power 1 times b to the power 1, and this is indeed true. So we shall now set our next iteration to be n equals k and assume that expression to be true. So we have n equals k, and then by substitution we shall have a times b all to the power k equals a to the power k multiplied by b to the power k. We shall assume this to be true and then set our next iteration to be n equals k plus 1. A times b to the power k plus 1 should give us, so using what we had from when we set our iteration to k, let's label it, let's say equation 2. Using what we had and then comparing it to this, you can see that if we multiply equation 2 by the expression ab, we are going to have ab of k multiplying ab, giving us ak or a to the power k, b to the power k, and then multiply by the expression ab. The reason why I multiply this equation 2 by 2 is that in example 1, I mentioned that one common trick is to write the n equals k plus 1 case in two parts, such that one part will look like when n is equal to k, what we have over here, which is assumed to be true already, and then the other part can be checked to see if it holds. So from what we have over here, we can see that we have a to the power k plus 1 multiplied by b to the power k plus 1, and that gives us the same thing on the right hand side, a to the power k plus 1 and then multiplied by b to the power k plus 1. Now we can see that the right hand side of our equation and the left hand side are equal, and so we've proven that by mathematical induction, or we've proven by mathematical induction that a times b all raised to the power n is equal to a to the power n b to the power n, and it's true for all values of n. So let's take a fourth numerical example. So from what we know, we shall set our n equals 1 for our first iteration. So we have 1 cubed giving us 1 on 4 times 1 squared, and this times 1 plus 1 squared. This is the same as 1 on 4 times 1 times 2 squared. And so this will give us 1. When n equals 1, this is what we have. Then we shall set our next iteration to be n equals k. So we have the expression 1 cubed plus 2 to the power 3 plus 3 to the power 3 plus 4 on and on plus k to the power 3, giving us 1 on 4 k squared multiplied by k plus 1 all squared. And then we assume this to be true. Then we go on to do for when n is equal to k plus 1. So by substitution, we shall have 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed on and on plus k plus 1 all cubed, giving us now we have 1 on 4 k plus 1 squared, and then we have k plus 1 plus 1, so k plus 2 all squared. Now we can see again that 1 cube plus 2 cube plus 3 cube plus 4 cube on and on till plus k cube is contained in this summation or in this sequence. And so by substitution, now we are going to have 1 on 4 k squared multiplied by k plus 1 all squared plus k plus 1 to the power 3 should give us 1 on 4 multiplied by k plus 1 squared times k plus 2 squared. So let's try and simplify. So now let's do the expansion. Let's expand further. We can now add like terms here. So we can see that the left hand side of our equation is equal to the right hand side of our equation. So now we've proven that 1 cube plus 2 cube plus 3 cube plus 4 cube plus 5 cube on and on plus n cube is equal to, we are proving that this is true for all values of n through mathematical induction. So we have proven through some 5 numerical examples the concept of principle of mathematical induction. Thank you for watching, and we hope to see you in our next tutorial session.